number systems, the focus of what we're doing right now. And so with number systems, there are many different number systems that are used worldwide, but we're only concerned with a few of them, and we're going to really narrow it down actually because you know, we have a limited amount of time, and this is just going to be a little bit of an introduction anyway. So the system that we're kind of used to, that's ingrained in us, is the decimal system. Okay, we use it every day. We start learning it when we're in kindergarten, and it's just instinctive for us to use base 10 or decimal. And so decimal is the one that we are very, very familiar with. Decimal, which is base 10. Now, we're going to actually take a look at 3 other number systems in our sort of study of this section, and they are going to be binary. Now, binary is a system that is widely used, of course. It's zeros and ones. This is digital information, anything to do with processors, computing, programming. So very, very common to see this system, and this is base 2. We'll also look at octal. Now octal, which we call is base 8 actually, base 8. Octal is a system that if you get involved at all in PLCs, you're going to see the application of this system. PLC inputs, outputs, for instance, numbered 00, 01, 02, 03, 04, 05, 06, and 07, and then they'll go to 10, 11, 12, and so on. So 0 through 7, and that corresponds to the octal system, okay? So widely used in PLCs. We're also going to explore hexadecimal. And this is base 16. The applications of this may be somewhat more limited, but if you ever work with troubleshooting equipment, many types of equipment generate fault codes in hex, and then you have to be able to cipher them and figure out what information is needed from those. Okay, so these are the 4 systems that we're going to look at and compare. And so what I want to do is, first of all, the very first thing is I want to say there must be some common ground between all of these systems. And there must be an essential element, something that if we can learn it for sure about one, we can apply it to the other systems. So this is a very important concept. So here's what I want to show you, and I believe this is it. The number of actual spaces that you have can be very small or very large, depending on which number system you're using. But what I want to do is I want to show you this box. I'm going to break this up into, I think it's going to be about 6 or 7. And it's going to be 7. Now, if I wrote a number into this, and I didn't tell you anything about the base, there are some things that you would automatically think. So if I said this is 1, 0, 3, 5, 8, 7, 2, most would look at that number and say, oh, that's 1,035,872. And you'd be right if that was a base 10 number, okay? And so what we have built in is we understand immediately when we see a number. If I say to you, what's the value of the 2? You know, the overall value of that 2. Oh, it's just 2. Why is that? Because it's in the ones place. You go, oh, so this is, anything here is times 1. Yeah. What is the value of the 8? Oh, that's actually 800. Well, that's because it's in the hundreds place. The 7 is in the tens place. making the 7 worth 70. The 1 on this end is worth 1,000,000. 1,000,000. And so on. This one here is 1,000, 10,000, 100,000. Okay? And so you see the way that we look at it. Now, the reason that we quickly come up with these numbers is because we have this deeply ingrained in our subconscious that this space is 1, this is 10, this is 100, this is 1,000, 10,000, 100,000, and million. Okay, we don't have to have anybody to sort of go over that with us. Now, the difference between the number bases is that in different bases, the value of each space is actually different than it is in base 10. And so we say to ourselves, okay, then there must be a formula or a system to actually determine that. And there is actually, and let me show you what it is. I'm going to take away this number to avoid it being a distraction, and I'm going to show you this. I'm just going to divide this into 4. This would carry on, but I want to start down here. Now, if I say that this is 10, base 10, right here, this is a base 10 number, and I want to know what is the value of that space, this position in the number. And we would call this the least significant number. Okay. And we go, well, the way that we actually determine this value is that we use the base and we go 10 to the power of 0. 10 to the power of 0, and anything 10 to the power of 0 equals 1. In the next space, we use the base, and the exponent is simply which space is this. So what I want to show you, and this is something you need to realize as you go through these numbers, this is essentially what we would call, I refer to this as bit 0, bit 1, bit 2, and bit 3, because the thing about it is that 0 is significant in these spaces as well. Mathematically, we have to realize this is kind of like the 0 spot, the 1, the 2, the 3, in terms of numbers of spaces. So 10 to the 0 equals 1. This one would be 10 to the power of 1, which is 10. So anything in here, any number you see in here will be multiplied by 10. This is 10 to the power of 2, which of course is 10 times 10, and that is 100. This is 10 to the exponent 3, to the power of 3, and this equals 1,000. Now, the interesting thing about this is now that you understand this is just exponentializing the base over the number of spaces, now you can see that's the key right there. We can apply that same thing to all of the systems. And so what we really need to do then is we need to look at the 4 systems, and we need to see what is the value as the spaces increase, what is the valuation of each space. And so what I'm going to do is we're going to do an example under each one of these bases, just so you can see how this works. All right, under the base 10 number. So I'll write them right in here. So this is 1, 10, 100, 1,000, and here is 10,000. Okay, so those are kind of the values that we would get by taking 10, and this would be 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. Okay, so we go, okay, let's go over then to this base number. I'm going to put this box down here. And let's go ahead and work our way through this. Now, if this is base 2, that means that if I look at these spaces, I say, how much is this space actually worth in terms of how many items can I count with that space? This is how we look at it. We go 2 to the power of 0, which equals 1. And so that means in this space, we can actually only count 1 item. In this space, we have 2 to the 1, which is actually 2. We can count up to 2 things in this space. Now in this one, we have 2 to the power of 2, which means this space is worth 4. So you see how we went 1 to 2, that was double, 2 to 4, that's double. Why is it double? Because our base is 2. So that means that this will be 2 to the exponent 3, which is 2 times 2 times 2, which is 8. 2 to the exponent 4, this is 16. 2 to the exponent of 5, which is 32. Now what you're going to notice is that these numbers are a little bit familiar. Just listen to them as I go up. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Sounds like I'm talking about the resolution of your big screen TV, doesn't it? And that's because these are binary, and those are the memory positions that occur in digital memory, zeros and ones. So you can see that the actual values of each space in the number go up by the exponent of whatever the base is. Now, let's look at it for octal. This is interesting. Now there's octal. I'll make about 5 spaces. Now, here we have base 8. This is 8 to the 0, 8 to the 1, 8 to the power of 2, 8 exponent 3, 8, 4. What this really actually means is 8 to the power of 0 is 1. 8 to exponent 1 is 8. 8 to exponent 2 is 64. 8 times 8 being 64. What's 8 times 8 times 8? And at that point, I probably got to grab my calculator. And I'll start running it through. So 8 times 8 times 8, 512. Okay, then I multiply that by 8, and I get 4,096. So you see how these numbers are, wow, these numbers are jumping. But stop and think about it. This is octal, right? So the base is smaller than it is in 10. So even though the value of any number that I would put into this space would be multiplied by 4,096, if I was in base 10, I would already be up to 1, 10, 100, 1,000, 10,000. And here I'm only at 4,096. So you can see that the actual density of octal is going to be lower than decimal, okay? Now, to finish our next example, let's go ahead and look at this one, which is hex. Now, hex, I'm not going to put too many spaces in this number because hex has a very, very high density. I'm going to put in about 4 spaces for us to look at. So 16, base 16, 16 to the power of 0 is 1. 16 to the power of 1 is 16. 16 to the power of 2, 16 times 16, I think it's about 256. And that it is, 256. And now we have 16 exponent 3, which is this times 16, and I get 4096. Now here's the interesting thing. In a hex number, each space, by the time I get to my 4th space, I'm up to 4096. in octal, I had to get 1, 2, 3. Oh, sorry. In octal, 1, 2, 3, 4. It was my 5th space before I got to this. So you can see that the density of this is higher. Density of the hex number is higher. Now that we have an idea of this value per position in a number, let's go ahead and take a look one by one at these bases, and I'm gonna show you a little bit how to calculate what the numbers will be, and then we'll talk about converting after that. So let me get rid of this. And of course, decimal, you know, we don't need as much review of that. So decimal is going to be over here. Okay, no problems there. I'm going to start with binary, okay, binary. Now, how do we count some numbers? How do we count in binary? And so I want to show it to you like this. There's something that we call the radix. And this word, radix, is equal to saying base. Okay, so the base. So when I say this is binary, that means it's base 2. When I say this is decimal, it's base 10. So this number, this 10 and this 2, this is described as the radix or the base, and there's something very, very important about it. What this number represents, and it's the same in octal and it's the same in hex, what this number represents is the number, it's the number of unique characters that are used. Okay. The number of unique characters that are used. And so again, just to clear this up, what are the unique characters that we use in the decimal system? Well, they look like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there you see 10 unique characters. Now, any number that you have in the decimal system is going to be made up of a combination of those characters. And so we say that the radix essentially is 10, and that means we have 10 unique symbols that we can use. So let's look at binary. What are the unique symbols that we can use in binary? Well, zeros and ones. And so if you see a 2 in binary, that's an illegal move, okay? All we can have is ones and zeros. And so if all you can have are ones and zeros, now I'm going to remove this, not because it's not important, because it is important, but I'm going to remove it because I just need the board space. Zeros and ones, all we have. But what do you have if let me just show you this. Okay, now many of you are going to recognize what these are as soon as I'm done drawing them, especially. I'm going to use nice dark lines. Okay, and I want to draw several of them. Okay, and these are, I'll put the defining features on them so you can see what they are. Okay, and by now I'm sure you know that these are yellow, number 33 Marets. Okay, and I have 1, 2, 3, 4, 5, 6, 7 of them there. Now here's the problem. If I needed to express this in a binary number, I would go, well, I can't use 7 because that's an illegal number in the binary system, okay? Doesn't work. So you go, okay, what am I going to use to number these? So you go, okay, well, let's start off. If you have if I didn't have any Moretz, I would say that that would be 0. And that would be a fair, that would be fair to say, okay? So 0 equals 0. 1 equals 1, okay? Well, now I've used up my symbols. Now what am I going to do? Well, remember, in a binary number, the spaces are like this. The first space is worth 1, the next one is 2, the next one is 4, and the next one is 8. So let's see what we can do here. If I have 2 Moretz, then what I have to do is I go, well, I can't use a 1, so this is going to flip back to being 0 again, and I'm going to put a 1 here. Now, if I look down here, if I have a 1 in here and a 0 here, that means that I have one group of 2, and I have one group of 2 and 0 in the ones. So that means I actually have, if this is one group of 2, then I have 2. So this number right here represents 2 in binary. And so we go, okay, what's 3? Well, it's going to be 1, 1. 2 plus 1 is 3. I go, oh, okay, now I'm getting it. What's a 4 going to be? Oh, the third place indicates 4. So this is going to be 1, 0, 0. And that will equal 4. Okay, so I go, okay, I'm going to get rid of the 7 because I know I don't even need it now. This is going to work perfectly. So I go 5. What's 5 going to be? Well, it'll be 1, 4, and 1, 1. And so I go, okay, 4 and 1 is 5. And so I don't want any of those, not yet. Now, if I wanted to count 6, I would go 1 of 4 and 1 of 2 and none of 1. So 4 plus 2 is 6. Now 7 is, this is what I wanted to count originally. I want to be able to tell you how many Moretz I had. And so what I'm going to say is, well, that's going to be 1, 4, 1, 2, and 1, 1. And that equals 7 in binary, okay? So you get the idea how we go with this. Now, we can continue counting on into very large numbers, and we're going to, but I just want you to get the idea that these numbers only make sense if you understand what is the valuation of each column. What is the valuation of each column in the number? So if you realize that the first column is 1, the next column is 2, 4, 8, 16, and so on, then whether there's a 1 or a 0 in that column just tells you whether, you can now start to see, okay, I can actually count some things with this and it's going to make sense. So what I'm going to do then is I'm going to go ahead and I'm going to show you a larger binary number, and I'm going to show you how to figure out what it is if we convert it, if we need to convert it to base 10 so we can kind of get our head around what the number is. How do we do it? So I want to get rid of this. And I'm going to leave this binary bit here just for a reminder of what we're doing. And here we go. I'm going to give you a binary number, and it's going to look like this. Okay, now that's not too large of a number. And so let me show you how I would convert this to base 10, just kind of on paper or on the board, okay? So take a look, watch what we do. I'm going to say that this 1 means that I have 1 of whatever this column is worth. So I'm going to go like this, 1 times, and I go, oh, that first column is worth 1, so this equals 1. Now I'm going to go to the next one. I'm going to go 0 times this column is worth 2, but seeing as this is a 0, this equals nothing. I'm going to now go to the next one. I'm going to say 0 times 4, well, that equals 0 too. 1, now by the time I get here, I'm at 1, 2, 4, 8. Now I have 1 times 8 equals 8. Now I have 1 times 16 equals 16. Now I have 0 times 32, which equals 0. And now I have 1 times 64, which equals 64. Now, if I go 64 plus 16, that's 80, plus 8 is 88, and I should say 89 base 10. So this number would represent almost a box of 100 morettes, right? 89 items would be represented by 1011001 base 2. And what you're going to notice is that to count this number in decimal, all I needed was 2 spaces. To count the same number of items in binary, I need 1, 2, 3, 4, 5, 6, 7 spaces. So notice the extremely low density of the binary number system compared to the decimal system. I'm going to continue with octal and hex, and we want to talk about the symbols that we can use, the unique characters that we can use in these systems. And so this is going to probably not be a huge surprise. In octal, we start with 0. We use 1s, 2s, 3s, 4s and 5s, 6s, and 7s. But we don't use anything beyond that. So if you see an 8 in a number, it's probably not an octal number actually, because it has to be between 0 and 7. Now, I'm going to have to write a little bit smaller, but let me show you what we'll use for hex, okay? I'll turn my cord around here. Okay, let's use, what are we going to see for hex? Well, we're going to start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I can't say 10, but I have 16 things that I need to basically 16 different symbols that I need. So I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm only up to 10, right? 1, 2, 3, 4, 5, 7, 8, 9, 10. So let me think about this. What could I write down to represent 10? And so I said, wait a second, why don't we just use the alphabet? So they go, okay, that works. A, B, C, D, E, and F. Now F, the value of F is easy to remember because it's 15. Okay, so F is actually equal to 15. We can't say 15 and we can't write 15 because that would be using a 1 and a 5, and so this wouldn't be a unique character. We'd be mixing these ones. So F doesn't appear anywhere else here, so F works great for 15. E is going to be just going back down, right? So E is 14, D is 13, C is 12, B is 11, and A is equal to 10. All right, so the unique characters in the hex system that we use to write numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And there's your 16 unique characters. So now you've got them all the way across: decimal, binary, octal, and hex. And this number, which we call the base or the radix, refers to the number of unique symbols, and there you see all of them right there. Okay, so the next thing that I'm going to talk about is what do we need to do with all of these numbers? What's our purpose? So what I'm going to do is I'm going to get rid of this real quick. And what I want to show you is what we're going to do with the number systems. For the most part, we like puzzles, okay? We actually like puzzles. And so when we see a number that is in some form that we don't immediately recognize, we like to decode it. Our minds immediately go to decoding information. It's just natural for us, and most people really enjoy it. So what we're going to do is we're going to say, we're going to do conversion. So let's say that we see a number and we say, here's a number that's in the decimal system, and let's change it to binary. Or we see a number in binary and go, I wonder what that would be in decimal, okay? And so we need to be able to do conversions back and forth. So I'll show you a list of the conversions that we're going to do. We're going to do 10 to 2, and then we're going to go from 2 to 10. Then we're going to go from 10 to 8, and then we're going to go from 8 to 10. Then we're going to go from 10 to 16, and then we're going to go from 16 to 10. Okay, now these are the core kind of conversions that we do. Then I'm also going to show you how to convert from directly, basically, from 2 to 16, and how to go basically from 2 to 16 and, you know, the other way. So 16 to 2, actually. All right. And then what we'll, you know, by the time we get through all of that, then we're going to be down to the point where we're just going to need to do some practice work. And that'll start looking pretty good after that. So, there's one more that I'll add here. So 2 to 16. We'll also go 2 to 8 and 8 to 2. So those are the conversions that we're going to cover. All right. These there's 1, 2, 3, 4. There's 10. Essentially 10 different conversions. Now I want to put you at ease. One way you can do is, of course, you can learn how to do this on your calculator. There are some limitations because, especially when you get into binary numbers, because of the low density of the binary system, you can wind up with some enormously long strings of ones and zeros. And most calculators will only handle about either 8 or 10 spaces of that. So it's good to know how to do it on a piece of paper. But obviously, you can do it whichever way that you like. But in terms of just understanding it, all of these conversions can be done pretty much with just 2 or 3 very simple processes. And as long as you understand them, it works really well. So the first process that we're going to use it to convert a number from 10 to 2. And this process is called division and remainder. Okay, so this is the first process that I'm going to show you how to do, division and remainder. Now, when we go the other way, when we want to go from a binary number to a decimal number, there's another process that we'll use, which is quite similar, and it's called place value and multiplication. Place value and multiplication. And so if we're going from 10 to another base, we use division and remainder. If we're going from other base to 10, then we use place value and multiplication. Now, the very first example that I gave you, we took a binary number and we found out that the base 10 number was 89. We used this place value and multiplication method. So that's the very first thing I showed you. Now, let me show you division and remainder, and it looks like this. I'm going to use a number that's not too large so that we don't fill up the whole board. So I'm going to start by using a number that is like maybe 227. 227, and this is a base 10 number, 227. And I want to know, what does this look like in ones and zeros in a binary number? So here's the process. Step number 1, divide your base 10 number. Step number 1, divide your base 10 number by your base. And so this is going to equal 113.5. 113.5. So what that really is saying is if I took 113 times 2 would be 226, and then I took 0.5 times 2, that would be 1, and that would be my 227. So what this really means is I have, my answer is actually 113 plus a remainder of 1. 113 times 2 plus 1 equals 227. Now the interesting thing is that this 1 is going to be the least significant number in my binary number. So it's going to go like this. We're going to go like this. I'm going to go down. I'm going to make a line across here. I'm going to bring it up and I'm going to put it here. And I'm starting a base 2 number. I'm starting at the least significant digit. I'm going to work my way across, okay? Step number 2, 113 divided by 2. Now that's got to be 50, 55, 56 would be 112. So it's going to be 56 plus 1. Okay, do you see where I'm going with this? This 1 is the remainder. And so I'm going to go like this. I'm going to bring it up right here. Okay, so I got a 1 and a 1. Now I'm going to go 56 divided by 2 is equal to 25 plus 3. It's 28. Now, is there any remainder? 28 times 2 is actually 56. So that means that my remainder is actually 0. Now, the remainder is what I'm concerned about. So this is going to become the third column in my binary number. Okay? Now, I'm going to take 28. I'm going to divide by 2. So this was step 3. Now I'm on step 4, right? 28 divided by 2, 14 plus 0. This 0 is going to go here, like this. It's going to go over here. It's going to go up. And my fourth place is going to be a 0. Now, I got to move over where I've got a little more space. I'm going to go actually, let me see. I should have moved those over to begin with. I'm going to draw it here, and I'll copy that over a little bit further over. Okay, here's going to be number 5, step number 5. So we're looking at 14. 14 divided by 2. That equals 7 plus 0 remainder. And so this 0, of course, carries down, goes across here, comes up, and it's right there. Okay, so now I'm down to 7, step number 6. 7 divided by 2 equals 3. So 2 times 3 is 6 plus 1. So now I have a remainder again of, it's 1 this time, so it's going to go down. I'm going to scoot this across, all the way across here. I'm going to bring it up here. Now we're looking at 1. So far I'm at 1, a 0, a 0, a 0, a 1, and a 1 here. Okay, so this number is starting to take shape. So I now have 3, step number 7. 3 divided by 2. That equals actually 1, and there's a remainder of 1. So I take the remainder, drop it down, run it across, and I bring it up here. 1. Now I'm not done yet, so be careful. I still have 1, and you have to keep dividing until you cannot divide anymore. So 1 right here. Step 8. What is 1 divided by 2? And you go, whoa, wait a minute. I can't do that. There, it doesn't work out. There's nothing. So it's actually 0. But if you don't have any of this, so you actually have 0 of that group of 2, you do still have a remainder of 1. And so this 1 actually becomes your most significant digit, and it's very important because it will actually be in the column that is worth the most. And let me give you an example of how much this 1 is going to be worth. Going across here, this is 1, 2, 4, 8, 16, 32, 64, and 128. So guess what? This 1 right here, this little remainder right here, if you don't do this step right, you miss the largest part of this binary number, and it's actually 128. Now, what we need to do in order to make sure that we didn't make any mistakes is this, and watch carefully what I do here. See, as these are all 0s and 1s, 1 times 128 is obviously just 128. So here's what I can do, okay? I'm going to take the number, and if it's a 0, I'm going to put it in red. So that's a 0. That's a 0. And that's a 0. And if it's a 0, it means that there's no number to add, okay? So we go like that. So now if I go, okay, that means if I just add 128 plus 64 plus 32, well, this would be 180, 192, 192, 194. That would be 224, right? 224, 25, 26, 27. So if you add these all up straight across, it equals 227. And that's how you justify that you actually did the correct divisions, okay? So there you see it. This is a 10 to 2, number conversion. All right, let's go ahead, and I've remade my list on the side here, so we'll keep track of where we're at. 10 to 2, okay, 10 to 2 and 2 to 10. We've actually done both of these. I just showed you a 10 to 2 conversion. The very first one that I showed you was a binary number 2 base 10, so that gives you an idea of where we're going with those. Now let's look at a 10 to 8. Now remember, 2 basic kind of methods, okay? And the methods are division and remainder. Division and remainder. And the other sort of method that you use if you want to convert the other way is place value, and multiplication. Okay, so there's sort of the one method, and this is sort of the other method. Now, we're going to start with this one. We're going to go from 10 to 8. So when you're going from 10 to any other base, that's when you use the division and remainder. So here we're going from 10 to 8. I'm going to use a little bit larger number this time. We're talking about larger bases. So let's start with the number 37,589. Now that's a legal number in the decimal system. Those are all digits that we're used to using and seeing. And so what I'm going to do is I'm going to just grab my calculator quickly, and we're going to work our way through this. Now remember, the first step is you take the number 37,589 and you divide it by 8. And this actually equals 4,698.625. Now, what I want to explain here is that this is actually very significant. What does that 0.625 mean? Well, what this means is we actually have 4,698 groups or divisions of 8. And then our remainder is only 62.5% of 8. And so if I go 0.625 times 8, that equals 5. This equals 5. And so that's actually my remainder right there. 5 is the remainder. So that means that over here, I'm going to make my base 8 number, and the first character is going to be 5. Now, let's see where we go from here. We're going to take this 4, 6, 9, 8, and we're going to divide it by 8. 4, 6, 9, 8, divide 8, and that equals 587.25. Now this one's a little easier. What does this 25 work out to in terms of a remainder? Well, it's 0.25 of 8. So that means 0.25 is actually 2. So that means that 2 is the next character in that number. Now, I go 587 divide 8. 587 divide 8. And that is 73.375. Now there's one I haven't seen, right? What is 0.375 times 8? And it actually equals 3. So these are our remainders, right? So they go over here. There's the 3. Now, I want to take my 73, and I want to divide that by 8. And this equals 9.125. So 9.125. Now 0.125 times 8 is actually 1. So that means that 1 is actually my remainder for this one. So there's a 1. Now we're down to 9 divided by 8 equals 1. And it's going to be, I'm guessing, 1.125. 9 divide 8 equals 1.125, which means 1 with a remainder of 1. 1 with a remainder of 1. So the remainder 1 goes up here. Now, I still have 1 that I have to deal with. So I go 1 divided by 8. What does that equal? We go, well, 1 divided by 8, it's just 1/8. And so really, I don't have any groups. This does not equal any groups of 8, but I do have, so it's 0.125, which means that my remainder is actually 1. Now, this is a very important step because this 1 represents the largest value in this number, and it's actually right there. Now you see that we've gone from a base 10 number with only 1, 2, 3, 4, 5 digits, and we've gone to a base 8 number with 6 digits. And that's because the valuation of each space in an octal number is a little bit less than it is in a decimal number. Very interesting to see these numbers develop, but you got to make sure you go right to the last step. So now I'm going to take this number and just as a double check, I'm going to show you how the place value and multiplication actually works. And so we can actually use this, first of all, to double check our answer here. And also it'll demonstrate this particular process. So we go 5 times 1 equals 5. 2 times, what is our second space in an octal number? It's 1/8. So 2 times 8 equals 16. What is our third space worth? 3 times 64. And so that's going to be 192. So the next one, we now have ones, 3 of them that are at 1. So it's going to be 1 times whatever that's worth, 1 times whatever that's worth, and 1 times whatever that's worth. So let's put these values in. So it goes 1, 8, 64. What comes after that? 64 times 8 equals 512. Times 8 equals 4096. Times 8 equals 32,768. 32,768. Now, seeing as these were all times 1, I can just add these up directly. But for instance, if that was a 5, that would be 5 times 32,768. So you can see that it would become, pretty significant to have that number in there, right? So this is 4096, and this is 32,768. Now what I'm going to do is I'm going to carefully add these numbers up. And so I've got 32,768 plus 4096 plus 512 plus 192 plus 16 plus 5 equals, and I got a button bounce, 5 plus 16 plus 192 plus 512 plus 4096 plus 32,768, and it's 37. So if I add all these up down here, this equals 37,589. Now, I see that that's the same number I started with, and so that means that my double checking was correct. And what it means, what this process shows you is that yes, this most definitely is the correct conversion to base 8, from this base 10 number, okay? So that's the process there. Now, let's go ahead then. So this is really how you look at division and remainder. This is from base 10 over to 8. And really, just if you double check it back using place value and multiplication, it totally tells you, first of all, if this number matches, yes, you did the right process, and this was certainly the right number. So it's a confirmation, works really well. Now, what I'd like to do is I'm going to move ahead into another base. For the next conversion, I want to convert from base 10 to hex, so base 16. And because hex is a very dense number system, it can handle huge numbers. I'm going to use a really large decimal number, a truly large decimal number to convert. And let me show it to you like this. I'm going to make this up on the fly. I'm going to say that this is 2,539,781. Is that right? 2,539,781 base 10, okay? Now you're gonna see this won't take very long to convert this into a hex number. Now a hex, like I said, is used in cases particularly where there are many, many different values, like tens or hundreds of thousands of different values that all need to have some kind of a unique code. And for instance, paint codes are expressed in hex. And you think about all the different shades of colors, and they all have their own code. So let's take a look at this. This is base 10. We want to convert this to hex, or base 16. So the very first thing I'm going to do is I'm going to divide this by 16. So divide by the base. This is step 1, okay? Step 1. 2539 781 divided by 16. And this equals 158, 736. 158, 736. That's my next number, but I do need to do this. It has, I'm going to move it over here a little bit. Here's the remainder right here, and it's the decimal on this, which is 3125. 3125. What is 0.3125 times 16? And then if you check that out, it's actually a 5. Okay, so there's the first character. Okay, so here's my hex number over here, base 16, and this is a 5. Now I'm going to go over here. This is the number to divide now. 158, 736 divide 16. This equals 9921. 9921. And that looks to me like that's a nice even division. So this is 0.0. So the actual next, the next character here is going to be 0. Now, if I take 9921 and I divide 16, that equals 620. 0.0625. Now 0.0625 is quite a small portion, so I'm going to go 0.0625 times 16, and it actually is a 1. Okay, so this is a 1, this one is a 0. 1. Now, this was step 1, step 2, step 3, step 4. Let's move now to step 5, and we're going to go 620 divide 16. That equals 38.75. 38.75. Now what is 0.75? 0.75 times 16. And as it happens, that is going to be 12, right? And so over here, we go, well, we can't write 12. So what we're going to do is we're going to write C, because C in the hex system is the same as saying 12. Now, step number 6. 38 divide 16. 2.375. So we now have 2 and 0.375. 0.375 times 16 is actually 6. So that means that here my remainder was 12. Here my remainder is 6. So now I've got a 6. 6C105. Now we're going to have another digit still, I think. Here's 7. What is 2 divided by 16? And we go, well, it's 0. We don't have the full 16, but it's 0.2 divide 16 is 0.125. Now, what is 0.125? 0.125 times 16. And it's actually 2. And so there you have it. The 2 is our actually most significant digit in our hex number. So 2,539,781 in decimal is actually 26C105 in hex. Okay, so there's your conversion. Look at the number of spaces, 1, 2, 3, 4, 5, 6, 7. Here you have only 1, 2, 3, 4, 5, 6. And also, you're looking at some, it's interesting just to compare and see the difference in how they look. Now, what would we do with this number if we, do we trust this? Is this definitely the right number? Is it the correct hex number? And so what we need to do is a little double check, and we'll do that double check. Over here, we used the division and remainder. Now we're going to use the multiplication, basically place value and multiplication. So let's do it like this. I've got quite a bit of space right here, so I'm just going to come this way. So we're going to go like this. I'll come all the way down here. And this is going to be 5 times 1. And this is going to be 5, right? This 0 is going to be actually times, this is hex, so this is going to be 16. Remember, this space here is 16 exponent 0. This is 16 exponent 1. This is 16 exponent 2, 16 exponent 3, 16 exponent 4, and 16 exponent 5 in terms of what is the value of the place, right? So 5 times 1, 0 times 16, 1 times, and what's 16 times 16? And I think we calculated earlier that it was actually 256. 256, but I'm going to double check that. 16 squared. 256, that's right. And we have one of those, so this equals actually 256. So far we have 5. That one was 0 because this number was 0. This is now 256 because this was a 1. This one's going to be interesting. Here we have C times, and what is the actual value? 16 to the power of 3. So we're going to go 16 times 16. This is 4096. 4096. Now 4096 is the place value. C is, remember, 12. So what is 12 times 4096? And we have 49,000. 49,152. 49,152. Very good. Now we're at 6. 6 comes over, and we go 16 to the power of 4. So we were at 4096 times 16. 65,000. 65,536. Now that's the value of the actual place. And we have this number times 6. And that's 393, 216 actual units. Now, in this one, we only have 2, and it is times, so we were up to, that one was 4096 times 16. And now we are at 1,048,576. That's the value of each unit in that column. So that's actually the column value. And so now we go, oh, well, we got a 2 in there, so we have to take that number times 2. And that gives us an actual number of 2,097,152. Now, what we need to do is we need to take this here, which is 2,097,152 plus 393,216 plus 49,152, and then we need to add 256 and 5. And thankfully, when I add all of those numbers together, I see that I have 2,539,781. And so you know, that now I can say, whew, okay, that's good, that worked out well. This was actually the exact correct conversion to a hex number, because now I've double checked it back using place value and multiplication, and that it worked out perfectly. Now I'm going to give you, at this point, we've done 10 to 2, and then we double checked it back to 10. We've done 10 to 8 and double checked it back, 10 to 16 and double checked it back. And so now what I'm going to do is I'm going to give you a little quiz. This is for you, this is going to be an online quiz, and it looks like this. I'm going to write 4 numbers in the different bases, okay? So this is going to be 4, 8, 6, 4, 9, 8. So that's base 10. This means that we have, 486,498. Then I'm going to write a base 2 number. This is going to be 1, 0, 1, 1, 1, 0, 0, 1. And I'll leave it at that. That's a binary number. Then down here, I'm going to write an octal number. Now remember, so here I'm good, right? Anything up to 0 to 9 is okay. Zeros and ones. You don't see any 2s anywhere in that number, right? Otherwise it wouldn't work. Octal numbers are tricky because when you're making them up, it's easy to throw 8s in, and you can only go as high as 7. So let's go with 7, 0, 1, 5, 3, okay? And this is base 8. Now I'm going to look over here and I'm going to do a base 16. I'm going to say this is going to be A3F17. A3F17, and this is base 16. Now, from all the information that I've given you so far, here's what I want to do. I want to ask you this a very specific question. For the base 10 number, how many actual items, if I was counting literally one of those, one of those, one of those, actual items, whatever they are, apples, morettes, acorns, doesn't matter, rice, whatever you want to count, how many actual items would be actually represented by the 6 in this number? And how many actual items would be represented by the 1 in this number? And how many actual items would be represented in binary by the 1 in space 4? Space number 4, so column 4, okay? I'm going to say 4, and remember these start at 0. These all start at 0. This is, so in other words, the 6 is actually in space 3. This 1 is in space 2. The one in space 4 is 0, 1, 2, 3, 4. It's this one right there. And what about the A? What about the A in this base 16 number? And that's actually in space 4. Okay, so this is 4 actually. I'll get rid of that. Okay, so if you look at the A, it's literally in space 4. This is in space 2. This is in space 3. 0, 1, 2, 3. 0, 1, 2. 0, 1, 2, 3, 4. So you see that space 4. This one, 0, 1, 2, 3, 4. Okay. Now, the question is, how many actual items are represented by the 6, by the 1, by the 1 in this space, and by the A here, okay? And
what I'm going to do is I'm going to take my calculator and I'm going to work out the answer to that. And I'm going to give you just a couple of moments, and then we'll come back and talk about the answer. Okay, we're back. And so what I've done is I wrote the answers up here, and hopefully you got this straightened out. If you're looking at this, the 6 in this number is in the thousands place. And so, 6 times 1,000, of course, 6,000. In this number, the 1 is in a column that is worth 64. Remember, this is 1, 8, and then 8 times 8 is 64. So the answer to this one, 64. Up here, remember, this is 1, 2, 4, 8, 16. And so there's a 1 in that position, that equals 16. This one, a little bit of a different story. The A, remember, is equivalent to 10 in terms of the symbols. And the valuation of this column is essentially 1, 16, 256, 4096. And this column is worth 65,536. And when you multiply that by 10, the answer is 655,360. So you should be able to look at a number, and really what this is about, okay, is do I really understand the place value concept? In other words, taking the base, exponentializing it, and finding out what the valuation of each column is, because that's a secret to being able to do number conversions and come up with the correct values. Okay, so what I'm going to do, I'm going to take this away, and we're going to go to the next conversions, which are just below there on my left, and we're going to look at them. Now, when it comes to binary numbers, they convert quite well, for instance, to octal or to hex. And let me show you, so directly, without going through base 10, without doing a calculation of base 10, you can figure this out quite simply. And so let me show you how the process works. If I have a number that is, let me show it to you like this. This is going to be an octal, okay? An octal number. So base 8. And what happens is the characters that I can use are 0, 1, 2, 3, 4, 5, 6, or 7. Now the question is, how many binary numbers would I need to show each one of these characters? And so the answer is, for 0, I only need 1. For 1, I only need 1. For 2, I would need actually 2 spaces, because this would be 1, 0. 3 would be 1, 1. Now when I get to 4, I would actually need 3 spaces, because that would be 1, 0, 0. A 5 would be shown by 1, 0, 1. A 6 would be 1, 1, 0. And a 7 would be shown by 1, 1, 1. Now, guess what? This is the largest symbol in the octal system. So that means that if I have a box that is separated into three segments, I can show a 7 like that. And so that means if I take a binary number and I divide it into groups of 3, then I can very quickly convert it to octal. So let me give you this example. I'm going to take a fairly large binary number and show you how easy it is to convert to octal. So I'm going to go with this. I'm going to go with 1, 0, 0, 1, 1. And put another 0, 1 there. 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 0. Now this would be a real mess to try and figure this out, divide this out and multiply it, place value, and things like that. So one of the easier things to do might be to convert this to, for instance, if you wanted to quickly convert it, take it straight to hex, but I'm showing you octal right now. So how do I convert this to octal? Well, I take this and I divide it into groups of 3. 3, 3, 3, 3, 3, and 3. So look at that. I have 1, 2, 3, 4, 5, 6. That means that if I convert this number to an octal number, I will only have six basically symbols in my octal number. And here's how you actually figure out what they are. This is quite neat. Put this into binary as though you were looking at a binary box that is like this. Okay, so here's my groups of 3. Remember, in binary, this is 1, this is 2, and this is 4. So we're going to create each segment here. We're going to create a value based on this. So here we see this number right here is going to be 6. 4 plus 2 is 6. Remember, this is what we're using. 4 plus 2 is 6. This is also going to be a 6. This is also going to be a 6. This is going to be a 5. This is going to be a 1. And this is going to be a 5. So that means that 515666 is actually the octal number that matches this binary number. And so very, very quick way to actually break it down. Now, in order to double check this, we would have to then take and, this will be a lot easier to boil down, for instance, than this binary number would be. So I could go like this. I could now say, remember, this is now an octal number. So I've gone binary to octal. Now I could just say 6 times 1. And I could say 6 times 8. And I could say 6 times 64. 5 times, I think it was 256, or is it 512? I better grab my calculator on that one. What is, just to double check, I don't want to steer you wrong. So we've got 64, 864, 64 times 8 is 512, yes, 512. So there's times 512. Then I have 1 times 1 times, the next one is going to be 512 times 8, 4096. And the next one is going to be 32,768. Okay, 32,768. And that's going to be 5 times that. So what I'm going to do is I'm going to write the numbers back over here. 1 times 6 is 6. 8 times 6 is 48. So I've now got 6 plus 48. 64 times 6 is 384. 384. 512 times 5 equals 2,560. 2,560. And that one was the 512 times 5. Now I have 4096 times 1, so that's just going to be 4096. And then I have 5 times 32,768. And that's 163,840. 163,840. And now if I add these up, I'm going to go 163,840 plus 4096 plus 2560 plus 384 plus 48 plus 6. That equals 170,934. Now, this should be a base 10 number, right? So we go, okay, so we converted from binary to octal, and now we've double checked this octal number, and it looks like it's about 170,934. Now, it would take a fairly good sized calculator to be able to input this number. You could do it with an online calculator probably. You could run this in and it should tell you the same value. But you know what I'm going to do? Just to do a double check straight from the binary, just to prove that this conversion works properly, let me show it to you like this. And this is exactly how I would do it. So this is kind of the long form, but let me show it to you like this. I'm going to start at the top with the least significant in the binary number, and it's 0, 1, 1. Then I have again 0, 1, 1. And then I have again 0, 1, 1. Then I have 1, 0, 1. Then I have 1, 0, 0. And then I have 1, 0, 1. Okay, so that's the binary number. Now, this will only take a moment, and let me show you the place values of these. This is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 20, 2048, 1024 is 2048, 40, 96, and now we're down to 40, 96 times 2, 40, 96 times 2 equals 8192. 8192 times 2 equals 16,384. 384 times 2 equals 32,768. 32,768 times 2 equals 65,536. 65,536 times 2 equals 131,071. 131,071. Now watch this, is kind of interesting. What happens is I can effectively take any number that has a 0 in front of it in this binary number, and I just get rid of it, because if there's a 0, then there's nothing there. Okay, so I'm going to get rid of these. Anything that has a 0, I'm going to get rid of. And now what I want to do is I just want to, this is 1 times each of these values. So let's double check. This is going to give us peace of mind whether we did this whole thing properly. Okay, so let's go here. 2 plus 4 plus 16 plus 32 plus 128 plus 256 plus 512 plus 2048 plus 4096 32,768 and down there 131,071. And look at that. $170, 9, 34. Now, I'm probably going to double check that again just to make sure it's right, but you know, that looks pretty good at that point. Okay. Now you guys are probably smiling to yourselves. You're thinking that was one off. I did make a small mistake, and I'm going to fix it right now. This was actually supposed to be a 2. And then that actually equals this number. So I was looking at my calculator and I'm thinking, what? How can I be one number off? So yeah, I miswrote this last number. It's 131,072, and that equals 170,934. So you can see that now we've looked at it 2 different ways, and we came to the same conclusion. So it kind of confirms it. I mean, how else are you going to know with this number, right? This is like this big crazy number. So You got different ways of working it out. This is the place value. This is the place value and multiplication method. This is converting it to another base. You know, so there's lots of different ways to look at these. So this is the base 10 number that we concluded down here. And so you can see that when you look at it several different ways and convert it back and forth, it should justify and it should make sense. Now, what I'm going to do then is I want to show you how to convert from an octal number to into binary. So from octal to binary. Okay, let's take a look. Now let's say I have an octal number that looks like this. I'm not going to make it too big. 6, 2, 5, 3, 3. Okay, so there you have it. Now what I would do if I wanted to convert this into a binary number is I would go like this. First thing, this is 8, right? I would take this and I would put a box right here. And I would take this, I'd put another box right here. I would take this and put a box right here. Now, how many characters have to fit in each one of these boxes? Well, we already just looked at this. Basically, if it's an octal number, 7 is the biggest one, and so we only need 3. So remember, the values of these are 4, 2, 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, and 4, 2, 1. So we're breaking literally this number and creating binary segments out of these. And this in turn will be our actual full-size binary number. Now, we're going to start with 3. That's going to be 0, 1, 1. Another 3, so another 0, 1, 1. A 5, 1, 0, 1. A 2, 0, 1, 0. There's your 2 right there. A 6, that's going to be 1, 1. So 4 and 2 is 6, and a 0 there. Now this would literally be the binary number that would match from this octal number. So 62,533 octal, now converted into a binary number. So it's a very pretty straightforward conversion when you do it in that way. Now the last one that we want to do is we want to now convert between binary and hex directly without having to use 10. So let me show it to you like this. I'm going to start by mentioning to you that we already know that we have 0 through F for a total of 16 symbols that we use, okay? That's what we have in the hex system. Hex, 0 to F. And so what we need to know is, what is the largest one? Well, it's F, and it's 15. What kind of a box of binary information do we need to build a 15? So let me show you the box right here. If I wanted to count 15 in binary, what would I have to do? Well, I go, you know, if I make this 1, 2, if I make it just 3, that's 1, 2, and 4. So I go 4, 5, 6, 7. That's not enough. So then I have to go 1, 2, 4, and 8. And I go, well, is that enough? 8, 12, 14, 15. So look at that. 4 spaces of binary information is enough to represent F. And that's the largest character I have in hex. And so let me show it to you this way. If we had, and I'm going to start I'll start with a binary number, okay? And so let's just look at it like this. Let's say that I have 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1.
binary. Now, what I need to do is I need to actually take this information and break it into groups of 4. So let's take a look. One right there. Oh, there's another one. There's another one. And there is another one. Now we go, that means that my hex number, if I convert this binary number to hex, my hex number is going to have 4 actual characters to it. And the characters will be, well, this one's going to be, remember now, 8, 4, 2, 1. So this one's going to be 5. This one is going to be 8, 9, 10, 11. So this one is going to be B. This is going to be 4, 5, 6, 7. That's going to be 7. This one's going to be 8, 9, 10, 11. So it's going to be B again. Remember, A is 10, B is 11. So we've got B7, B5 is the hex conversion of this binary number right there. And so actually very interesting the way that conversion happens. And let me show you, I'd like to show you one that goes the other way. This, by the way, if you want to pop this into your calculator, it's easy to put in a hex number and convert it to decimal. Calculator handles that no problem. It's the binary numbers that you have a lot of trouble with because they're so huge. And you know, the only reason that ones and zeros work so well for computing is honestly, and many of you are aware of this, if you think about back in the day, you think about how much faster everything has gotten. It used to be when you sat down and you wanted to do something on the computer, you would wait and wait and wait. And it was because actually handling all those ones and zeros took a long time. The only reason now that we don't notice it so much is because of the ridiculously fast speeds, the gigahertz of speed at which the data is being transferred. But ones and zeros, in terms of how much, what is the massive amount of numbers that you have to pass to put together some usable information, you know, it's incredible. It's only because it's so fast that it's doable, okay? But the numbers themselves are actually huge, huge strings of data. Now, let me just show you this one. I'm going to make one up on the fly here. Let's take a look at it. This is going to be my hex number. I'm going to make it 8 A 7 F 2 9. 8 A 7 F 2 9. And so what I'm going to need to do is remember, now we just talked about this, each one of these is going to need actually 4 pieces of information of binary. And so here I had literally 4. Now I've got 1, 2, 3, 4, 5, 6. So I'm just going to need more boxes, and they're going to look like this. 1, 2, 3. Put another one here. 4, 5, 6. And I think we're still on. Camera there. Yes. All right. So I'm going to start at this side. Honestly, it doesn't matter where you start. Just draw a thing down so you know which box you're looking at. Okay. So the 8 is going to go in as 1, 0, 0, 0. The A, this is actually 10. So this is going to go as 1, 0, 1, 0, right? 8 plus 2 is 10. This one is going to go in as 0, 1, 1, 1. F is going to go as 1, 1, 1, 1. Remember, it took the whole thing, 8 plus 4 plus 2 plus 1 to make 15. 2 goes in as 0, 0, 1, 0, and 9 goes in as 1, 0, 0, 1. Now look at that binary number, how large it is compared to this hex number. So there's 16, this is the base 2. Okay, so I think that gives you the general idea in what we're doing in converting back and forth between these numbers and getting a good understanding of place value. So I think the best thing to do at this point is I want to show you one more thing. And so I'm going to clean the board up and I'm going to show you in just a moment what this looks like. All right, the last thing I'm going to show you today is this is a little bit of a, it's something that's interesting. It's not actually a number system. It's called an encoding system. Encoding. And what this is, it's very, very similar to, it's quite similar. It's definitely involved in, sort of number theory, but what it is sometimes in some applications, what you want to do is you want to take the decimal system and you want to be able to pass digital information very quickly about the digits specifically. And so for instance, in multi-segment displays, electronic displays, for instance, that display different types of information where the numbers change very quickly, can be common to use BCD. And BCD is called, there's the short form, BCD, and it's binary coded decimal. Okay, so this is a coding system that is only used, basically it's very specific, it's right in the name. This is used for taking a base 10 number and encoding it into ones and zeros. Okay, but this is not the same as the binary number system. Okay, this is different. So what we're really looking at is this. In BCD, what we do is we look at each of the unique symbols in the decimal system, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and we generate a 4-digit piece of code for that. And this is how it looks. Remember, it's binary coded decimal, so it's going to look a lot like binary. But this is BCD, okay? BCD. And it looks like this, 0, 0, 0, 0. Now, each one of those is significant because this chain, it's read in blocks of 4. So you have to see that those 4 zeros mean 0. These 4 pieces of information mean 1. These 4 pieces mean 2, and so on. Okay, but every bit of this is important in the code. So let me give you an example. I'm going to continue through. This is going to be 0, 0, 1, 1. This is going to be 0, 1, 0, 0. This is going to be 0, 1, 0, 1. That's 5. This is going to be now we're up to 0, 1, 1, 0. That's 6. This is going to be 0, 1, 1, 1. This one is going to be 1, 0, 0, 0. And now you know why we need 4 pieces of information of code, is because to get up to the 9, 8 and 9, you need the whole 4 spaces, right? And so 9 is 1, 0, 0, 1. Okay? So these pieces of information are strung out in a chain. But let me show you this, and this is interesting. I'm going to clear this off. I'm going to make a number that's not too big. Something like this. I'm going to use the base 10 number 578. 578. Now, how would I take this number and show it to you in BCD? So here's what I want to do. I want to take this, I'm going to put it into BCD. So I need a box, piece of information for each one of these. So the 5 is going to be 0, 0, 1, 0, 1. Okay. The 7 is going to be 0, 1, 1, 1. And the 8 is going to be 1, 0, 0, 0. Now here's the interesting thing. In a piece of BCD code, you cannot just leave off this 0. Must be there. Now, in a binary number, you never start a binary number with 0. You always start it with a 1, because a 0 would just be nothing. You don't even, if it's 0, it's insignificant. It doesn't need to be there. In BCD, that 0 is actually important. And just to show you, I want to show you how this would differ. What I'm going to do is, this is the BCD for this number, 578. What would binary be for 578? And so let me show it to you like this. So I'm going to go 578 divided by 2 equals, and that's going to be, I'm going to grab my calculator just to make sure that I get this right. This is going to be 578 divided by 2 equals 289. And it actually equals 289 even, so that's plus 0. Then I'm going to go with 289 divided by 2 equals 144 plus 1. Okay, and then I'm going to go 144 divided 2 equals 72 plus 0. Then I'm going to go 72 divided 2, and that equals 36 plus 0. And then I'm going to take 36 divided by 2 equals 18 plus 0. Then I'm going to go 18 divided by 2 equals 9 plus 0. Then I'm going to go 9 divided by 2 equals, and that must be 2 times 4 is 8. So it's going to be 4 plus 1. Then I'm going to go 4 divided by 2 equals 2 plus 0. And then I'm going to go 2 divided by 2 equals 1 plus 0. Now, I'm not done yet. I have to try and divide this last thing. So I go 1 divided by 2 equals 0 plus 1. So what are my, I take all my remainders, which I've put over here neatly on the end. Okay, these are my remainders right here. Right there. And remember, this is going to be the least significant digit, and this is going to be the most significant digit. So if I wanted to write this number out, I would write it like this. I'm going to write the binary number right here beside the BCD number, so you can see that they're actually quite different things. So this is going to be 0, 1, 0, 0, 0, 0. So I've got 0, 1, 0, 0, 0, 0, 1, 0. Got 0, 1, 0, 0, 0, 0, 0. Sorry, I got 0, 1, 0, 0. Got 0, 1, 0, 0. That takes me up to there. 0, 0, 1, 0, 0, 0, 1, 0. That takes me up to there. And I'm left with a 0, 1. And this is the binary number. So don't be confused. There's between the two, you can see this actually has a different number of digits. Here we've got 12 pieces of information in this code. Here we've just got 4, 8, and 10. Okay, so binary does not equal BCD. This is a different thing. All right, and so in terms of numbers, I think what we really need to do now is we need to just do some practice. And so you're going to find in the handout section just below, you're going to find some number problems to work through. And I think by the time you're done doing that, you should be pretty confident.
don't leave doing it by hand, doing that hand method of division and remainder, just to make sure you know how to do it by hand, because every once in a while the calculator will let you down and you do need to actually work it out on a piece of paper, all right? So that's good for this section.